Hey Justin, here's a quick overview of what we did in class on for section 2.5. So hopefully this will clear up whatever confusion you have, but of course if you still have questions then let me know. So section 2.5 is about population dynamics, and we studied three basic kinds of population growth. Populations can grow exponentially, logistically, or via a threshold. And so um, exponential growth we dispense with kind of quickly, but for any other kind of growth that you want to analyze, there are two questions you need to answer. And here are those two questions. Given a differential equation that's modeling a population, what are the equilibria of that differential equation? And once you know the equilibria, you need to be able to classify their stability. So if you did that pre-class assignment, you know what an equilibrium solution is. But even if you don't, we'll go over what these two things mean. So what an equilibrium is and what it means to be either stable or unstable. But as you go through the homework, any sort of population question, these are the questions you ask yourself, because the equilibria and their corresponding stability will tell you everything you want to know about how the population is growing. Okay, so keep that in mind. Equilibria and their stability tell you pretty much everything. That's the upshot of this section. So just real quick, what does exponential growth looks like? Exponential growth occurs when the rate of change of the given population is proportional to the population itself. So the way you would translate that into an equation is the rate of change, dy dt, is, right, equals proportional to the population. So dy dt is proportional to. So proportional to meaning basically equal, but you pick up a proportionality constant that's positive in this case. So what you're really saying is, hey, find me functions whose derivatives are basically themselves, except you pick up a constant coefficient, and the solutions are exponential, as the name might suggest. So if you are modeling a population whose rate of change is proportional to the population, you're just going to get exponential curves modeling that growth. And so, of course, populations of bacteria or whatever will grow exponentially in the short term. So in the short term, bacteria in a petri dish satisfy this equation that their rate of change is equal to some proportionality constant times the current number of bacteria. Okay, so in exponential growth, the growth rate is a constant. So here this R is a growth rate. In practice, it's not realistic that your growth rate will remain constant at any given time. It's more likely that your rate of change will change over time. This growth rate will change over time. And so in logistic growth, we let the growth rate change over time. It's now a function of the current population. So now we have a linear function right here. That's a coefficient of y as opposed to a constant function times y. Now you have something linear times y. So the idea, of course, is just that, well, suppose it's not constant, what's sort of the next step up from that? And the next kind of function up from a constant function is a linear function. So here's a logistic growth model. The rate of change is y, so the current population, times a linear function of y. So that linear function of y is giving you your growth rate, more or less. And in this case, that constant k is called the carrying capacity, and we are assuming that r is bigger than 0. R has a special name. It's called the intrinsic growth rate, not just the growth rate. This sort of overall linear term is kind of the growth rate now. So what are the equilibria of this system? Well, an equilibrium is simply a constant solution. That's what you learned from that pre-class assignment. So to find constant solutions, you're looking for solutions to this dE whose rate of change is 0. Right? Because if you are a constant solution, your rate of change is 0. You don't change if you are constant. So to find the equilibria of any dE, not just this one, you would just substitute 0 in for y prime and see what you get. And, in this case, you have a factored quadratic in terms of y, and you get two solutions. Y equals 0 will work, and y equals k will work. So if you substitute a k in for that y, you'll kill this term here, and you'll get 0. Okay, so here's a specific example. Y prime equals r times 1 minus y over 6 times y. The equilibria of this system are y equals 0 and y equals 6. Again, you could have found that by plugging 0 in here, substituting 0 in for y prime, and just noticing that, oh yeah, y equals 6 kills this, y equals 0 kills this. So those are the equilibria of your system. So, so let's look at a picture of this before I move on. Okay, so let me just graph the two equilibria first. There's y equals 6, there's y equals 0. Now let me turn on the slope field of that dE. That's kind of messy. Okay, so you'll notice in the slope field a couple of things are happening. First of all these lines are flowing towards y equals 6. And they're actually running away from y equals 0. Let me zoom out. All right, you can see that effect more pronounced now. These arrows are all up-ticking and flowing towards y equals 6. And these are all down-ticking, right, towards y equals 6. And all of these other arrows down here are moving away from y equals 0. So in this system, solutions will tend to flow towards y equals 6, and they will tend to flow away from y equals 0. So let me turn off the slope field for a second, because in your homework, on your exams, you won't be able to draw slope fields using technology. You won't have this with you. So let me talk about how you could have predicted this kind of behavior. Here's my dE, right? What you could think about is like, here's a y value of 1 right here, right? There's y equals 1. You could ask yourself, okay, if my initial population is 1, which means I'm right here, should I expect my population to rise or fall? Well, if y equals 1, you can plug 1 into this equation here. Right? You can plug y equals 1 in for y right there, and you would get r, which is positive, times 1 minus a sixth, which is positive, times 1, which is positive. So if you're sitting right here, you're expecting your slope to be positive, which means you'll rise. And you'll rise to, let's say, y equals 2, right? So you've moved from y equals 1 up here to y equals 2, whatever. Now you could plug y equals 2 in here and do the same thing. You would have r times y minus 2/6 times 2. So all that is still positive, which means you will continue to rise. So anyway, my only point is that if y lives between 0 and 6, so you have any sort of y value in this box here, between the red line here and the orange line here, any of these values, you would expect your graph to rise, which again, we already knew from looking at the slope field. These arrows go up. On the other hand, suppose you're up here. You say you're at y equals 12. Well, if you come back here and plug 12 in for y, notice now you have r, which is positive, but now you have 1 minus 2, which is negative, times 12. Right, so the overall effect is to create something negative, which means your slope will be negative. And so again, you can see if y is bigger than 6, then now this inner term right here is negative, which will force your curve to fall. So that's how we could have predicted a picture like this. If we're above 6, if our y values are above 6, we'll fall. If our y values are between 0 and 6, we will rise. Okay, so the technical language here is y equals 0 is called unstable, y equals 6 is stable. So what it means for something to be stable is that things flow towards it. To be unstable means that things flow away from it. So in this picture here, you can clearly see that y equals 6 is stable because things are flowing towards it. So if you remember the point of the section is that, hey, here's a differential equation. If you want to know things about what solutions are doing, all you need to know are the equilibria and know whether or not they're stable. And you can see why that's the case now, because now that we know that y equals 6 is stable and 0 is unstable, we now know that solutions will flow towards y equals 6, and they will flow away from y equals 0. So if this is modeling a population of whatever, deer or something, we now know that extinction when the population reaches 0, we know that that's unstable. So we would expect deer populations to flow away from that. We would expect them to flow towards 6,000 or whatever the units are, individuals in that population. So real quick here, the reason K is called the carrying capacity, as you can notice from this picture, if we start with more than 6,000 deer, the population will fall. So the idea is that there just aren't enough natural resources around to support a population more than 6,000. So the carrying capacity really is sort of like a cap on population growth. If we start with less than the carrying capacity, we expect to grow up to that. So there's sort of like enough natural resources around to support growth up to this orange line. But if we just go into this forest and dump 12,000 deer in there, we would expect a lot of them to starve, about half of them to starve, and then sort of level out at 6,000. So that's the idea of logistic growth. Threshold growth is the same, except notice I changed, for notational purposes, I changed this K to a T for threshold, and now I've slapped a negative out front. So I still have a linear function here times y, I've just changed the sign of it, now it's negative. So this y right here will be positive now from the negative. So anyway, it's just it's sort of the opposite of logistic growth by slapping a negative on there. Notice though that when you put an a negative out here, that doesn't change when y equals 0. So y equals 0 it doesn't change when y prime is 0. Sorry. So if you plug in a 0 here for y prime, notice that, this should say a t. I forgot to change that. But in any case, the equilibria are found the same, right? Still y equals 0, still y equals t in this case. But what does change, the effect of slapping a negative there, is to change the stability. So here's the exact same equation I had a second ago. So this is with, what is it? Yeah, I'm going to take this equation that I just graphed for you and do the threshold version. So hopefully it looks like this now. So here's still y equals 6, here's still y equals 0, but notice now the arrows flow away from y equals 6, and they flow towards y equals 0. So in this setting, extinction is stable. If I start with like 2,500 or whatever the units are, right? But if I start with 2.5 in my population, rather than rising up to the carrying capacity, I'm predicting that in the long run they're going to go extinct. For whatever reason, the population doesn't have enough to sustain itself. But I'm predicting that if my population starts with more than 6 individuals, so maybe 10,000 or something, I'm predicting like really shooting up, right? So exponential growth. So the reason that these models are called threshold is because I'm basically saying, look, there's sort of this minimal floor that your population needs in order to get going. But once it achieves that floor, right, in this case 6,000, the population can take off and grow just fine. Okay. So all that said, here's a sample question they did in class. So the population of striped bass in a lake has been shown to be modeled by this equation. Notice this is logistic with intrinsic growth rate 1. The R value is a 1 out here, where y is measured in thousands. Okay, so we could, of course, just point out that the equilibria here are y equals 0 and y equals 2. So since this is a logistic equation, we would expect the population over time to converge to about 2,000 individuals. Because in logistic growth, the non-zero equilibrium is stable, and so and extinction is unstable. So if we start with 300 bass in this setup, so ignore this sentence for a second, right? Just ignore that. In this setup, if we start with 300 bass, we would expect to grow towards 2,000 over time, because that y equals 2 is the stable equilibrium. Okay, but in this case, we don't just have logistic growth. We have fishermen that are going to pluck fish out of there at a rate of 100 fish per day. So the question is, now what do you predict will happen to the population over time? And so I can tell you what the students in class said. Since y equals 2,000 was an equilibrium when you took this out, right? If you would delete that sentence, y equals 2,000 is an equilibrium. then if you're removing 100 fish per day, I suppose you would expect to converge to 1,900 fish as your carrying capacity. That certainly stands to reason. So let's see if that's what happens. Anytime you make a tweak like this, you have to construct a new differential equation that takes this piece of data into account, and here's how you can do that. So the fish are still growing like this, but now we're removing 100 fish a day from the lake, and since things are measured in thousands, I can't write 100 here, I have to write a 0.1. But anyway, so here's my fish per day number that I'm removing. It's just a constant, right? 100 fish per day, full stop, right? There's no percentage of the population being removed or something. Here's my new differential equation that will model what happens to this population over time. So if you want to analyze this, again, recall that the upshot of this section is that if you want to know about that DE, you can now find the equilibria and classify them. So finding the equilibria means substituting 0 in for y prime, solving the resulting quadratic. I skipped that because you are supposed to know how to solve quadratics. You can just use the quadratic formula or whatever. And now we have two new equilibria. One of them is not extinction anymore. It's actually, okay, so things are measured in thousands. So this is saying that y equals 10 is an equilibrium. So it's actually possible if you start with 10 fish, you can remain at 10 fish in perpetuity. That's kind of odd, but that's what falls out of this. But the more relevant equilibrium for us is this one, y equals 1.9899. So this removal of 100 fish per day took the y equals 2 equilibrium from up here and barely nudged it. It budged it by, basically a 100th, right? Which I guess you might expect. But at the very least, this does not fall to 1.9. Right, the students in class predicted a fall from y equals 2 to y equals 1.9 because you're taking 0.1 away. It actually doesn't fall that far. It barely moves at all. And so now if we look at a picture of this, what is this? So here are my two equilibria. Y equals 0.01 is indistinguishable from the y-axis, and y equals 1.99. Now when I turn on the slope field, you can see what it's doing. Yeah, this is a bit deceptive. Let me zoom in. See, these arrows are converging right to this line. They're trying to get you to 1.99 or 9899, right? Oops, let me 899. Sorry, let me zoom out again. So basically, when I've zoomed out too much, it doesn't quite know what to do with these arrows that are approaching that line. So when you zoom in, you can really see how they're really trying to get to that 1.9899. In particular, again, if you took the logic of the students from class, you would expect 1.9 to be the equilibrium. You started with 2, and now take 0.1 out of it. But notice the fish actually surpassed that. They grow almost back to 2. So basically, fish that grow like this are good enough at reproducing quickly to overcome most of this 100 that are taken out. There's like enough reproduction going on and enough natural resources in the lake to let the fish kind of just surpass this, right? Just really recover from this really quickly. So anyway, hopefully that cleared things up for you. This exercise is how we ended class that day. And so again, let me just remind you, this is the big takeaway, right? If you want to know about any DE in this section, so DEs that look like this, look like threshold, look like modified logistic or threshold, whatever, right? You want to know about those things, you need to do two things. Given a differential equation, find the equilibria, and then determine stability. So in this case, right, this y equals 1.9899, whatever, that's stable. So you can see the stuff is going towards it. Okay, so anyway, just let me know if you have other questions.